My name is Tyler Jones, and I'm a principal engineer here at Snowflake. Today, we're going to cover Snowpipe streaming and how Redpanda uses it to stream data via Redpanda Connect to Snowflake tables in high throughput, low latency fashion. To give a quick intro about myself, I'm an engineer here at Snowflake, and I work on all things streaming. I've been a member of our streaming efforts from day zero, and I'm currently the tech lead on a feature known as Snowpipe streaming, which we'll go into great detail today. So let's get started. Snowpipe streaming, what is it? So Snowpipe streaming is a feature that we offer at Snowflake that enables high throughput ingest into a destination table. We support throughputs of up to gigabytes a second for a target destination table with P99 latencies of 5 seconds or less. Ordering is preserved as part of this ingestion flow, so data appears in the table as the order was presented to a client. We support exactly once ingest as part of this feature. And we also support ingest from many, many sources. So the idea is that you can have thousands of clients streaming into a table in high throughput, low latency fashion. Data, once ingested, should have no restrictions. You could update this data, delete this data, and even insert data alongside of this newly ingested data via any of your other ingestion mechanisms. Insert statements, copy statements, what have you. This is designed to be an easy to use feature. Simplicity is a core feature principle that Snowflake has, and we wanted to follow these principles as part of developing this feature. And it's also worth calling out that this is a very, very secure feature. Data is preserved, or security is maintained, whether it be encryption, TLS, whatever, at multiple phases of ingest throughout the stack. And this feature does allow for error handling, and that we do surface different errors that you can handle depending on how you want to do that. So some key concepts for the Snowpipe streaming feature. The first concept that we have is a client. So this is simply an application or service running outside of Snowflake that runs an instance of the Snowpipe streaming client SDK. The Snowpipe streaming client SDK, in turn, is a Java-based SDK that acts as the interface to stream data to tables over what is known as channels. A channel, in turn, represents a logical connection from a client to a destination table. The way that we like to think of these is that they're sort of roughly analogous to Kafka topic partitions, albeit these are much more dynamic in nature and they are named. So a client could say, open up a channel named foo to a table bar. And once a channel is opened, a client has exclusive write access to that channel. So if you have a client A and a client B, and client B reopens up a channel that client A previously owned, client B gets exclusive write access to that channel. Writes to these channels are asynchronous. So when you put data into a channel, it will take some short time, usually seconds, before this data is visible in the table. One thing that these channels do support is the notion of an offset. This is an opaque string that you can use to reason about ingest progress on the Snowflake side. And we'll get into more later as to some examples as what you would use for offsets. So some key interfaces offered by the Snowpipe streaming client SDK. There's 4 key interfaces that I wanted to call out today that we're going to use as the basis for this talk. The first 2 are client level interfaces. The first is to open up a channel to a given target table, and the second is drop channel, where you can drop the channel that was recently created. The other 2 interfaces that are going to be very important is the insert rows interface, which is done on a per channel level. So with this interface, you can present a batch of rows that you want to stream into a Snowflake table. And for a given batch of rows, you can provide an offset token. So once these rows are ingested, this offset token becomes available via the second channel interface that I want to call out, which is the get latest committed offset token, wherein if you call this API, you will get back the last offset token that was committed in Snowflake. So as you periodically call insert rows with an offset token, and these rows gets ingested, the offset token will reflect the latest offset token for a batch of rows that was committed. So if we visualize what these concepts look like here, we have 2 clients where both of them are receiving incoming data. And the first client on top has a channel open to channel 1, or has a channel open to table A called channel 1, and a channel open to table B called channel 2. The second client has a channel 3 open up the table B and a channel 4 open up the table C as well. Now in this example, The second client here could say open up channel 1 to table A, and the client on top here would have its rights discarded by the protocol. So this is all well and good, but let's talk about how this works. To give a quick technical overview of ingest from end to end, we start with the client SDK, where it'll buffer data for some short period of time or a size threshold, depending on the throughput, and it will generate files known as BDEX, along with metadata about those files that it will then send to the Snowflake service. BDEX are simply blobs of interleaved encrypted Parquet data. They're comprised of what we call chunks of per table data that get registered to different tables. A question that often comes up is, what does BDEX stand for? And it is basically streaming ingest blob translated to French. I apologize to the French speakers. I cannot do the accent, so I'm going to not pronounce this aloud. So once these BDEX are written to a cloud storage location and metadata is generated for them, including things like min and max, null count, so on and so forth, what is referred to as expression properties, we send the REST request with that metadata and the file references to Snowflake. Snowflake, in turn, will buffer this metadata on a per table basis for a short period of time, where it then commits that information to a table. Once these BDEX are committed to a table, they're immediately available to query, which enables the low latency ingest. Now, for Snowflake native tables in the background, we will periodically migrate from the BDEX format to Snowflake's own internal data format, which is known as FDN. For Iceberg tables, which we also support ingest into, there's no need to migrate, so we're already in Parquet data. But you could certainly have something like clustering, DMLs, or what have you, copy rows from one set of files to another, depending on what you are doing with that table. So the client SDK, to talk through very quickly how things look like. So what happens is that as you open up channels to a table, we will take data on a per channel basis and buffer that for the given table. So in this example, you could see that we have, say, table A, or channels open for table A and channels open for table B. We will buffer that data, and then we will decide to flush to a BDEC. By default, it's after 1 second, but you can configure this with the max client lag, or if you hit a certain size threshold for the truly high throughput cases, where it makes sense to flush the data more frequently. Once we flush the BDEC, we will see that we have a blob that roughly is laid out with encrypted table A and encrypted table B chunks. The keys used for encryption are derived from table level keys, and we diversify these keys at read time to ensure that we can actually decrypt the data here. So there's no scenario in which if you query table B, you could actually access table A's ADA or vice versa. Now, on the service side, what happens after the client SDK sends a REST registration to Snowflake with the blob reference and the metadata for that blob? First, as I said, we write the BDEX to cloud storage, and they get persisted. The second then is we send these file registration requests to Snowflake. We have a front-end tier that will receive these requests from a client, and it will do things like authentication, authorization, making sure that you have the insert privilege into a table. It'll do table existence checks, so on and so forth. After we do some form of validation, we will actually shard to a backend service that we run that can reason about data, tables, and things like that. So we actually forward these requests to a service that's sharded by table ID. This backend tier will receive this data, and it will do some relatively lightweight set of checks. So some basic metadata validations, like making sure the EPs are sane. It'll do some channel level checks to make sure that the channel that's being written to is still like the active version of that channel. But then it will add these to an in-memory buffer. And it will acknowledge back to the client via the front-end tier that data has been received, but it's not yet committed. If the buffering tier goes down at this point, that data is lost and the client needs to replay it. It's sort of equivalent to the ACK is equal to 0 acknowledgement that Kafka offers. So at this point, when the Snowpipe Streaming Client SDK gets back this acknowledgement, it'll continue to send more data. From its point of view, ingest is done, and the caller would need to call the get latest committed offset token to reason about was this data ingested or not. Now, in the backend, what will happen after a short period of buffering this outstanding metadata is that we will attempt a table commit. And we will go forward with the table commit. And at that point, we will do some heavier checks to make sure the channels are valid, the EPs look good with respect to the current table metadata, so on and so forth. Assuming the commit goes forward and things look good, we will create a new table version in Snowflake. And at that point, that data becomes available to query. Ingest is effectively done. Now, what happens when you query this data is that after it's been registered to the table, we will simply reach out and fetch these BDEX and add them to the query. So that way you have lower latency ingest where you're hitting the BDEX directly. File migration may take place as needed and convert it to Snowflake's own internal format if it's a Snowflake native table. But you could certainly have the case where you have both a mix of FDN files and BDEC files, and you could query both. They would both be part of your query plan. And for these situations, we refer to the table as a mixed table because it's made up of multiple different file formats. So this is all well and good, but how does Redpanda use Snowpipe streaming to ingest data into Snowflake? So Redpanda has an incredible offering called Redpanda Connect, which is a declarative data streaming service which allows you to specify sort of inputs to outputs with transformations in between. Behind the scenes, what Redpanda offers is the ability to use Snowpipe streaming to send data to Snowflake tables after applying whatever processing steps that you want to have. And at a high level, the way that Redpanda Connect achieves this is by mapping topic partitions to channels and using the offset tokens to achieve exactly what's ingest. So what this looks like at a high level is that you could have incoming data coming into your topic or a generic Kafka topic, what have you. And you could have multiple partitions here. In this example, we have partition 1, 2, and then say you could go up to n. What Redpanda Connect will do is that it'll create a channel per partition that it uses to send data to destination tables for. And it will maintain on a per channel basis what was the last committed offset that it read from the Kafka topic partition. So if we visualize what this could look like, if we start reasoning about, what things look like on a per topic partition basis, let's say that we have a topic partition here with 4 records in it and some incoming data. So we have records with offsets 0, 1, 2, 3, so on and so forth. Redpanda Connect will start, and it will open up a channel corresponding to this topic partition, and it will position itself at offset 0 here. It will then call insert row, or insert rows, with the record corresponding to this offset 0 and use 0 as the offset. It'll then call insert row with record, the next record, and an offset of 1. But let's say that Redpanda Connect crashes, or there's rebalancing or something like that, right? And it may have been in the process of sending the record corresponding to the second offset. Redpanda Connect, at this point, we need to reconcile what was sent and what was persisted to reason about where it needs to reposition itself so that it doesn't send data twice. So what will happen is that it will reopen up the channel, and it will say, give me the latest committed offset token for that channel. And Snowflake will return the offset of 1. That was the latest persisted offset corresponding to the data that it sent in the past. And we guarantee as part of this protocol that no in-flight data at this point will be committed. So when 1 gets returned back, Redpanda Connect can safely reason about, okay, this is where I need to reposition myself to send data again. So it will then reset itself to 1 plus 1, for offset of 2, and start sending data from there on out to Snowflake, and that's how exactly once ingest is achieved. And one thing that I wanted to mention before closing out is that Redpanda Connect, we're very happy with the integration that Redpanda has achieved with this. They use the SDK and the interfaces that we expose, I think, in really unique ways. And I'm really proud of what they've achieved with what we've built. So it's been a joy to work with them and to see this integration happen. And that's it. Thanks for listening in and joining the talk. You can find me with this email here, tyler.jones@snowflake.com, or you can find me on LinkedIn. Thank you so much for your time.